Hello friends, welcome to my channel. This is Isro question paper, strength of material, part 1, complete solution. I will do it from 2006 to 2016. Question is PLQ by 3I is the deflection under the load P of a cantilever beam, length L, modulus of elasticity E, moment of inertia I, the strain energy due to bending is dash. Data given, deflection, it's PLQ by 3 EI. We know strain energy U half P into delta. Area of P versus delta curve, strain energy. Delta already given, so put the value of delta half P into PLQ by 3 EI. So P square LQ by 6 EI. From option B is the answer. You can do in another method, that also I am saying. For cantilever beam, P is the load, L is the length, moment is P into X. So strain energy is integration of 0 to L m square by 2 EI dx. 0 to L P into X square by 2 EI dx. It's equal to P square by 2 EI, take outside, 0 to L x square dx, integration of x square dx. If you do the integration, 2 EI x cube by 3, 0 to L. So P square by 2 EI into L cube by 3 minus 0. So finally we will get by 6 EI. That same B is answer, same answer we will get. Next question. A short column of external dia D, capital D, and internal dia small d carries an external load W. The greatest eccentricity which the load can have without producing tension on the cross section of column is. Its derivation is very lengthy. Directly remember that here because it's very repetitive in nature. This question 3 times in asked Isro, and IES also same question was asked. In other examinations also it's asking, so it's better to remember that formula itself. Its answer is C. Derivation also I am doing here. Here it's a short column. Here this is the short column, hollow section, internal diameter small d and external diameter big D. P is the eccentric load, E is the eccentricity. Here if we add two loads P and P, they will balance each other. So here this P and this P, they will form a clockwise couple. In next figure I will show that one. In this question asked no tensile stress. here that column if you add two loads we'll get one moment and one compressive load here. That same eccentric load can be derived as like this: clockwise moment m, its value is P into E. Here one compressive load P, internal dia D, small d, and external dia capital D. Here this side the column will bend like this, and this side compressive. So this side bending stress is positive and axial compressive stress is negative. Here both are negative. So in this question no tensile stress, so left side only it will come, this area somewhere it will come. We have to find the value of E, eccentricity, how much we can give. Again I am drawing that one. Compressive load and bending moment. Sigma B minus sigma A, axial compressive load P M P into E minus sigma B minus sigma A. So if you take left side, for zero tensile stress, sigma left side minus sigma A, it should be 0. And axial compressive stress sigma A is, we know it's load by area, so it's P by pi by 4 capital D whole square minus capital D square minus small d square. And here bending equation we know sigma B by Y equal to M by I equal to E by R. From there, so sigma B equal to M by I into Y maximum. So bending stress will get sigma B bending stress. M is P into E, moment of inertia for hollow, pi by 64 capital D to the power 4 small d to the power 4 into Y maximum outer dia by 2. Here already we got, so put the values sigma B minus sigma A equal to 0. It means sigma B equal to sigma A. Here bending stress equal to axial stress. Already we have got sigma B equal to P into E into 64 divided by pi into d to the power 4 minus small d to the power 4 into y maximum outer die by 2 equal to your axial stress 4p by pi d square minus small d square. Here pi gets cancelled, then p also cancelled, then 2 into 64, it's 32, 4, 8. Here we will get E equal to d to the power 4 minus small d to the power 4 divided by 8 into d square minus d square. You can use that formula. A square minus b square equal to a plus b into a minus b. Here d to the power 4 is square of d square. So d equal to d square plus d square into capital D square minus small d square by 8 into capital D square minus small d square. Cancel this one. One d by 2 we missed here. This one, this d by 2. It should be here. D. And finally E equal to d square plus d square by 8d. Same answer I got. This is very, very important for all examinations. Just remember that formula. In IAS conventional paper, they may asked this one. For that derivation is required, otherwise you just other examination you just remember the end formula. Next question. If the radius of wire stretched by a load doubled, then its Young's modulus will be A B doubled, B halved, C become 4 times, D none of the above. Young's modulus, this one, it's a material property. So you cannot change this one. So here none of the above is the option. Next question. Longitudinal stress in a thin cylinder subjected to internal pressure is, this is thin cylinder. This is very, very important for all exams. GATE also 3-4 times asked. IAS every time it's asking. Isro also 4-5 times this question was asked. Or other examination also this is very, very important. Mainly thin cylinder. Subjected to internal pressure. Hoop stress or circumferential stress is PD by 2T, and your longitudinal stress sigma L is PD by 4T. Here in this question, longitudinal stress in a thin cylinder, it's sigma C by 2 is PD by 2T into 1 by 2. We'll get PD by 4T. This is sigma L. So longitudinal stress is half of the hoop stress. A is the answer. Both formula is very, very important. thin cylinder, circumferential stress and longitudinal stress. Next, maximum deflection in cantilever due to pure bending moment M at its end is how much? Cantilever beam length is L, pure bending moment at its end M L. This is also very important for all examinations. Even if GATE, IES, Isro, Coal India, SEL, all examinations, this is very important. A, B. Slope at B is both slope and deflection both are important. ML by EI and deflection at B is ML square by 2EI. So in this question, maximum deflection asked. Maximum deflection is at B, at the extreme end. It is answer 2. Answer A, ML square by 2EI. If Poisson's ratio for a material is 0.5, then the elastic modulus for the material is, this is also very important for all exams. In GATE also this question is asked. These three formulas are very important. E equal to E is Young's modulus, D is modulus of G is modulus of rigidity, then K is bulk modulus, equal to 3K into 1 minus 2 mu. Mu is your Poisson's ratio. Here in this question, we use this formula, first formula. E equal to 2J into 1 plus Poisson's ratio given 0.5. So it's 2G into 1.5. It's 3 into G. Elastic modulus for the material E equal to 3 times the shear modulus. A is the answer. The bending equation is written as, this is also very important. Sometimes that long type question also, conventional question also, you have to derive this one. Everything you should know. I is moment of inertia, M is moment of resistance, here sigma B or F bending stress, Y is distance from neutral axis, E is Young's modulus, R is radius of curvature. Here we know to E by R. So then instead of sigma B, F is given M by I E by R. From option, it's square no, m by equal to this is also square, not question. C is the answer. Thank you friends for watching my video. If you like my video, then subscribe it and share it with your friends.